We all know that AI is getting incredibly powerful, but have you ever stopped to think about the cost? It's astronomical. But what if there was a different way? A way to get that same power, but by working smarter, not harder. That's exactly what we're diving into today, a genius architecture called Mixture of Experts.
So, to really get why this is such a huge deal, let me ask you something. Just take a guess. How much raw computing power do you think goes into training one of these massive, state-of-the-art AI models that we all hear about?
Okay, get ready for this because the answer is pretty staggering. For Meta to pre-train its Llama 2 models, it took a reported 3.3 million GPU hours. Now, to put that into perspective for you, imagine you had 1,000 of the best GPUs money can buy and you ran them nonstop, 24/7. It would still take you about 134 days just to get that one job done. That right there is a huge, huge bottleneck for the entire field of AI.
And that leads us right into our first big topic, what the industry calls the AI scaling problem. And believe me, this isn't just about the cost. It's about a fundamental wall we're starting to hit in how we build these amazing things.
You see, for a long time now, the main idea in AI has basically been bigger is always better. Just throw more data, more parameters, more computing power at the problem, and you'll get a better model. But we're hitting a wall. That approach just isn't sustainable anymore. The costs, both in time and in actual money, are getting so high that it's locking out almost everyone except for a handful of mega corporations.
So, the big question is, how do you get around that wall? Well, this is where things get really clever. A brilliant new approach to the architecture itself is changing the game. It's called Mixture of Experts, or just MoE for short.
So what is a Mixture of Experts model? Well, at its core, it's a completely different way of thinking about how to build a neural network. You know, instead of having one single gigantic model that has to know and do everything, an MoE model is more like a team of smaller, specialized expert networks. And here's the secret sauce. For any problem you give it, it only wakes up the exact experts it needs for that one task.
I think the best way to understand this is to think about doctors. A traditional AI model, what we call a dense model, is like one generalist doctor who tries to be an expert in, heart surgery, brain science, and skin conditions. I mean, they might know a little about everything, but it's super inefficient, right? Now, an MoE model, that's like a whole hospital full of specialists. You've got your cardiologist, your neurologist, your dermatologist. When you walk in with a problem, you don't have to consult every single doctor in the building. No way! The front desk sends you only to the one or two specialists who actually know how to help you.
Okay, so that sounds great in theory, but how does this team of specialists actually work under the hood? Let's get into the mechanics. We're going to look at what's called a sparse MoE model, and the process is honestly just incredibly elegant.
It all boils down to about 4 key steps. So, first, your input. Let's say it's a word, which the model sees as a token. It enters this MoE layer. Step 2, and this is the crucial part, a little network called a router looks at that token and instantly decides, okay, which of my experts are best for this job? It then picks just a small number of them, say 2 out of 8 available experts. Then, step 3, only those 2 selected experts actually fire up and do the computation. The other 6, they just sit back and save their energy. And finally, the results from those active experts are combined together to produce the final output. Simple as that.
And really, the magic is all in that third step. It's a concept called sparse activation. That's the whole key. Because you're only using a fraction of the model's total brain power for any single calculation, you get the benefit of a gigantic model, but with the computational cost of a much smaller one. It's genius.
Let's put some real numbers on this to see how powerful it is. The famous Mixtral 8x7b model is the perfect example. Now, on paper, it has a whopping 47 billion parameters. But here's the kicker. For any single piece of information passing through it, it only ever uses about 12.9 billion of them. So you get the vast knowledge of a 47 billion parameter model, but the speed and the cost of a model that's less than a third of the size. That's a huge win.
All right, so this brings up a really cool question, right? If you have all these different experts, what do they actually specialize in? Like, does one become the grammar expert and another the history expert? Well, let's take a look inside Mixtral to find out. Some researchers at NVIDIA were wondering the exact same thing. So they did this awesome experiment. They took Mixtral and threw 57 different academic subjects at it, everything from math to law, and they just watched to see which experts the router would pick for each topic. And what they found? Well, it showed clear, undeniable signs of specialization.
Just look at this. For example, when they fed the model problems about abstract algebra, super complex high-level math, it consistently turned to two specific experts, Expert 3 and Expert 8, over and over again. They basically became the go-to math whizzes of the group.
But check this out. The moment they switched the topic to professional law, what happened? The model pretty much ignored experts 3 and 8, the math guys. Instead, it lit up a totally different expert, Expert 4. It's like the model was saying, okay, this is a legal question, I need to send this to my lawyer.
Now, what's interesting is that the system is designed to try and spread the work out evenly, so one expert doesn't get totally overloaded. But as the NVIDIA researchers pointed out, when you give it a bunch of questions all on one specific topic, you get this large distributional imbalance. In plain English, that just means the model can't help but send all the work to the specialists for that topic. It's proof that this specialization isn't just a fluke, it's a real emergent property of the system.
Okay, so let's zoom out for a second. This is all super cool, but what does it actually mean for the bigger picture, for the future of AI?
Well, it really boils down to a few huge benefits. With MoE, you get way more model power for the same amount of computer juice. That means we can train more capable models, but faster and cheaper than before. For you and me, the end users, that means things like lower latency, you get your answers from an AI faster. And as we just saw, it leads to this incredible organic specialization happening right inside the AI's brain.
Of course, the story isn't over. This is still a super active area of research, and one of the biggest challenges right now is perfecting that router, the traffic cop of the system. The big goal is to make it even better at balancing the workload between the experts, so none of them get bogged down, while also making sure it always picks the absolute best specialist for the job so you don't lose any accuracy.
And that really leaves us with one final and I think very important question. For so long, the most powerful AI has been locked away, only accessible to those with astronomical budgets. But if this whole smarter, not harder idea really takes off, what happens when that kind of power isn't just for the giants anymore? What kind of incredible new possibilities in science, in business, in art will that unlock when this level of AI becomes available to, well, everyone?